Address and port translation behavior. There has been considerable variation in the way NAT operate. Most of the details relate to the specifics of the address and port mappings in figure 7.5. A NAT's address and port behavior is characterized by what is mapping depend on. The inside host uses IP address, port, capital X, X to contact capital Y1, etc. So the address and port used by the NAT for these associations are X1 respectively. We discussed this in the previous video. If x1 equals x2 for any y1, y2, the NAT has endpoint independent. And if x1 and x2, etc., the NAT has address dependent mappings. And if etc., the NAT has address and port dependent mappings. A NAT with multiple external addresses, i.e. where x1 may not equal x2, has an address pooling behavior of arbitrary if the outside address is chosen without regard to inside or outside address. Alternatively, it may have a pooling behavior of paired, in which case the same x, capital X1 is used for any association with y1. So in figure 7.5, we use the notation x, capital X colon small x to indicate that a host in the private addressing realm inside host uses IP address x with port number small x for ICMP. The query ID is used instead of port number. The IP address x is ordinarily chosen from the private IP address space defined in RFC 1918. So it's the same IPv4 for address. To reach the remote address or port combination, capital Y colon small y, the NAT establishes a mapping using an external, usually a public, globally routable address, capital X1, tick, and port number X1 tick. So assuming that the internal host contacts capital Y1 colon Y1 followed by Y2 colon Y2, the NAT establishes mapping capital X1 tick colon small x1 tick and capital X2 tick colon small x2 tick respectively. In most cases, capital X1 tick equals x2 because most sites use only a single routable IP address. So basically, the common behavior for this is not having two public IP address but just one public IP. So that's the normal NAT behavior. The mapping is said to be reused if small x1 tick equals x2 tick. So the port is preserved if that's what it means because the small letter is the port. If small letter x1 tick and x2 tick equal x, the NAT implements port preservation mentioned earlier. So the port preservation meaning if the NAT use the same port that the end device is requested in facing the public or when sending it through the public to the public internet, it is said to implement port preservation. In some cases, port preservation is not possible, so the NAT must deal with port collisions as suggested in the in figure 7.4. So here, a basic IPv NAT left rewrites IP address from a pool of addresses and leave port numbers unchanged. So that's port preservation. However, in this case, on the right side, it's not possible. NAPT must sometimes rewrite port numbers in order to avoid collisions. In this case, the second instance of port number 23479 was rewritten to use port number 3000 so that returning traffic for 192.168.1.2 could be distinguished from the traffic returning to 192.168.1.35. Table 7.1 and Figure 7.5 summarizes the various NAT port and behavior based on definitions from RFC 4787. For all common transports, including TCP and UDP, the required NAT address and port handling behavior is endpoint independent. A similar behavior is recommended for ICMP. For the UDP and TCP, which we discussed, they use an endpoint independent. So they don't use the address, though it also exists, and the address port dependent. So table 7.1 announces overall behavior is both its translation and filtering behavior. So to discuss the behavior of UDP or TCP, you really need to discuss the address independent, because that's the normal filtering, meaning if the public interface contacted this host outside, it will be able to contact any incoming packets. So that's the normal behavior for easier sessions over the internet. If you implement like the address or the address port dependent, those are not really typically used in current internet protocol. So here, each of these may be independent of host address, dependent on address, or dependent on both address and port number. So for independent, these are the less strict. The dependent, lesser than address and port number, because for address and port, you will only be able to contact that if the same port responds back or acknowledge or send a packet back with its corresponding port, address and port. Now, so basically you will be able to contact that network in the internet with an IP that has those networks. So whether it's implementing NAT, etc., you will be able to contact that if you just have the IP of the NAT or the public IP address. Kind of like in NAT traversal, which we will discuss in the next video. If you just have those public IP, you will be able to traverse within the private IP address inside the NAT. So the purpose of this requirement is to help applications that attempt to determine the external address used for their traffic to work more reliably. So the purpose of that is to work more reliably instead of cutting sessions in and out. We discuss this in more detail later when we discuss NAT traversal. As stated previously, a NAT may have several external addresses available to use. The set of addresses is typically called the NAT pool or NAT address pool. Most modern to large-scale NATs use address pools, but for low-end, they usually use one public IP, which is within the router, or within one public interface like Converge or PLDT. Note that NAT address pools are distinct from DHCP address pools discussed in Chapter 6. So the address pools is distinct from DHCP because DHCP kinda recycle that IP address within the network. But with address pool, you really have different address for different servers within the private NAT. We will discuss that server later. Although a single device may need to handle both NAT and DHCP address pools. Though a single device could do all this, they could have multiple address while at the same time is running a DHCP server. One question in such environments is that when a single host behind the NAT opens multiple simultaneous connections, is each assigned the same external IP address called address pairing or not? A NAT's IP address pooling behavior is said to be arbitrary if there is no restriction on which external address is used for any association. It is said to be paired if it implements added pairing. So again, when a single host behind the NAT opens multiple simultaneous connections, is each assigned the same external IP address. So every host within the private NAT open multiple simultaneous connections and each assigned same external IP. It is called pairing. So basically, kind of like the low-end router. This is how most router works in the world. So it is called pairing because you only have one public IP for all of those private hosts, and that's the recommended. Pairing is the recommended NAT behavior for all transports. If pairing is not used, the communication pair of an internal host may erroneously conclude that it is communicating with different hosts. For NAT with only a single external address, this is obviously not a problem. So if pairing is not used, the communication pair of an internal host may erroneously conclude that it is communicating with a different host. So if you have multiple IP or public IP with that same network host, it may be confused with the other when it is sending. For NATs with only a single external address, this is obviously not a problem because you don't need to map everything to each device, so there's less confusion, especially for nested NATs that we will discuss in the future video. A very brittle type of NAT overloads not only addresses but a very brittle type of NAT overloads not only addresses but also ports, called port overloading. In this case, the traffic of multiple internal hosts may be rewritten to the same external IP address and port number. This is a dangerous prospect because if multiple hosts associate with the service on the same external host, it is no longer possible to determine the appropriate destination for traffic returning from the external host. So, aside from just addresses or having a hard time to find those specific addresses for different addresses within the private NAT, there is also called port overload, where the protocol or port used for that protocol or the traffic of multiple internal hosts may be rewritten to same external IP address and port number. So if that port is not preserved, meaning that the CGNAT or NAT actually rewrites to this same port for all of the requester, this could be a problem. This is a dangerous prospect because if multiple hosts associated with the service on the same external host or multiple private hosts within the private network of this external host has the same port or service like TCP, it's no longer possible to determine the appropriate destination for traffic returning from the external host. For TCP, this is a consequence of all four elements of the connection identifier: source and destination address and port numbers being identical in the external network among the various connections. Such behavior is now disallowed. So that's the reason also why TCP has these four elements. We have source, destination, and port numbers to be able to distinguish it from other service that is being requested inside the network, private network. So that's also how the router was able to return back the packet to the device that sent it within a Wi-Fi or home router. Some NATs implement a special feature called port parity. Such NATs attempt to preserve the parity, evenness, or oddness of port numbers. Thus, if small x1 is even, small x1 tick is even, and vice versa. Although not as strong as port preservation, such behavior is sometimes useful for specific application protocols that use special port numbering, like real-time protocol abbreviated RTP has traditionally used multiple ports, but there are proposed methods for avoiding this issue. Port parity preservation is a recommended NAT feature, but not a requirement. So port parity or maintaining the evenness is a recommended NAT feature. It is also expected to become less important over time as more sophisticated NAT traversal methods become widespread. So the NAT traversal, we will discuss that in the future video, but as those become prevalent, this port parity may not be kept, though it is used for some protocol like RTP, and also it is used to kind of like solve that port problem, or same port, rewriting the same port for all the private hosts, though like port preservation resolve that now. So usually we will use quick in most of the services we use, like in videos. So this is not a problem, but for some like messages we still use TCP. So we need to understand how TCP session actually work. So it use this endpoint independent behavior to make sure the reliability, and it's connection and oriented. So once the session got like connected, so I mean that this only a problem with non-TCP or other ports that may implement not so strict session, like three-way handshake, because for TCP you really need to have a session to be able to communicate with the other server, and you only need the address of that network. So yeah, basically you don't need this port preservation, because you have this unique session that's also a consequence of the four elements it has: the source and destination address and port numbers. So that's also the reason why it has maintained this session, to avoid getting confused with other session contacting the same server within the private network. Filtering behavior. When a NAT creates a binding for a TCP connection, UDP associations, or various form of ICMP traffic, not only does it establish the address and port mappings, but it must also determine its filtering behavior for the returning traffic if it acts as a firewall, which is the common case. The type of filtering NAT performs, although logically distinct from its address and port handling behavior, is often related. So the address and port handling, there's a nuance as we will discuss in the previous video. They are related. In particular, the same terminology is used: endpoint independent, address dependent, and address and port dependent. A NAT's filtering behavior is usually related to whether it has established an address mapping. Clearly, a NAT lacking any form of address mapping is unable to forward any traffic it receives from the outside to the inside, because it would not know which internal destination to use. So one of the key in its filtering is usually with address mapping, because remember it should have memory or should be able to map the session with that forwarding traffic. Otherwise, it would not be able to communicate with the inside, because remember, it's rewriting its IP address. For the most common case of outgoing traffic, when a binding is established, filtering is disabled for relevant return traffic. For NATs with endpoint independent behavior, as soon as any mapping is established for an internal host, any incoming traffic is permitted regardless of source. So, for example, you open your Wi-Fi, and one of the services you use, for example, your browser, already have established mapping. So you're connected to the internet. Any other like notification that you may receive from other apps, as long or other service or other process, will be received now, because there's already an outgoing scene or outgoing UDP depending on the service you've created or you've connected. So as long as there's a mapping in the session, that's what address independent means. So address dependent, meaning that you need to contact that network or the the network address, IP address first, before it is able to contact your host. So you need to contact that specific address on the internet. It's not like one of the services of your laptop, for example, must contact one of the address on the internet. It's not like that. It needs to contact that specific address. That's why it's address dependent. For address and port, it needs to contact that specific address and the port of the host inside that address you're trying to contact. So it's related with server behind NATs, which we will discuss later, because sometimes you want to provide a service, so you will need to have a port inside the private NAT. So that's actually how you provide service using, for example, when you deploy your own application, etc. For NATs with endpoint independent behavior, as soon as any mapping is established for an internal host, any incoming traffic is permitted regardless of source. For address dependent filtering behavior, traffic destined, by the way, that address independent is how most NATs for TCP and UDP works, which is like 80% of traffic of the internet. For address dependent filtering behavior, traffic destined for capital X1 colon small x1 is permitted from capital Y1 colon Y1 only if capital Y1 had been previously conducted by capital X1 colon small x1. So the IP address and the port, of course, you need the service inside or port protocol to be able to contact, whether it's TCP, UDP, etc. That's why it's the transport layer. So most application usually choose this, either UDP or TCP, to contact each other. For those NATs with address and port dependent filtering behavior, traffic destined for capital X1 colon small x1 is permitted from capital Y1 colon small y1 only if capital Y1 colon small y1 had been previously contacted by capital X1 colon small x1. The difference between the last two is that the last form takes the port number small y1 into account. Server behind NATs. So if the host with address 10.0.0.3 is to provide a service to the internet, it cannot be reached without participation from the NAT for at least two reasons. First, the NAT is acting as the internet router, so it must agree to forward the incoming traffic for 10.0.0.3. This is also the reason why you have a problem of NAT traversal, because it needs to rewrite it Second, and more important, the IP address 10.0.0.3 is not routable through the internet and cannot be used to identify the server by host in the internet. So another reason is it's not routable because you did not set the IP for security purposes to avoid um, I think that's port something. There could be some issue with that if you expose your IP because someone could like contact you or your host. That's why these not though they are complicated to deal with, they are also important because it provides that firewall. Not anyone can contact you, but you also have to work around that. Instead, the external address of the NAT must be used to find the server, and the NAT must arrange to properly rewrite and forward the appropriate traffic to the server so that it can operate. This process is most often called port forwarding or port mapping. So the port mapping, we've been doing that previously, where the NAT translate the port from the outside or the packet. If it's rewriting the port, it will translate it back to the internal port that requested it. So that's the port mapping or port forwarding. With port forwarding, incoming traffic to a NAT is forwarded to a specific configured destination behind the NAT. By employing NAT with port forwarding, it is possible to allow servers to provide services to the internet even though they may be assigned private non-routable address. So this is also how you deploy application or how you contact, for example, someone with address dependent or address port dependent outside network as long as you have the IP address. This is what we've been talking. The reason for that is sometimes you need to provide a service through port called port mapping, where the NAT, you don't necessarily have this public IP, but you provide service through that public IP because you initiated port forwarding through your NAT. Port forwarding typically requires static configuration of the NAT with the address of the server and the associated port number whose traffic should be forwarded. So the way to actually implement this is, you guessed it, through memory or through static configuration by saving those static or that address inside to a associated port number, so that when not receive those kind of traffic, it will allow that using its public IP address, and then it will route it or translate it or route it to your host or to the actual private non-routable address with that specific port. So that's what we call static configuration. The port forwarding directive acts like an always present static NAT mapping. If the server's IP address is changed, the NAT must be updated with the new addressing information. So it must be updated as well, because otherwise the outside won't be able to contact that private non-routable IP. At the same time, you need to update it, so the bar for updating it is more strict, because again, if no mapping, it won't be able to contact by outsiders. Port forwarding also has the limitation that it has only one set of port numbers for each of its IP address transport protocol combinations. So because there's also weakness with the static configuration in which you only have one set of port numbers for each of its IP and protocol. For example, if you want to provide TCP protocol or service to this IP, you need to be able to have multiple public routable IP address, which, as you know, is limited or exhausted already. So your provider, or you will likely pay for a huge amount for that extra IP. So that's actually one of the limitations. So if you do this in cloud, it's the same thing that will happen. If you need to buy your own IP, it will cost more, and then you just share it with other networks. Thus, if the NAT has only a single external IP address, it can forward only a single port of the same transport protocol to at most one internal machine, i.e. it could not support two independent web servers on the inside being remotely accessible using TCP port 80 from the outside. Hairpinning and not loopback. An interesting issue arises when a client wishes to reach a server and both reside on the same NAT. NATs that support this scenario implement so-called hairpinning or NAT loopback. So if you want to contact the host in the same, for example, home Wi-Fi, you want to contact your own or other device, this is a scenario is implemented in so-called hairpinning or NAT loopback. For example, if X1 knows the private addressing information, capital X2 colon X2, there's no problem because the connection can be made directly because it's outside of your NAT. For example, you're contacting Google or YouTube. However, in some cases, you want to contact your device within the same network, or X1 only knows the public address. For example, you contacting your other device within your Wi-Fi through some outsiders first, like public IP, for example, your Converge public IP through their site, managing your device there, etc. In these cases, capital X1 attempts to contact capital X2 using the NAT with destination capital X2 tick colon small x2 tick. The hairpinning process takes place when the NAT notices the existence of the mapping between capital X2 tick colon small x2 tick and capital X2 colon small x2 and forwards the packet to capital X2 colon x2 residing on the private side of the NAT. So the NAT will notice that there's a mapping between the capital X2 or the outside, the public address and the inside, which is X2, and it will route there from the public to the private instead of connecting directly privately. Figure 7.6, a NAT that implements hairpinning or NAT loopback allows a client to reach a server on the same side of the NAT using the server's external IP address and port numbers. That is, capital X1 can reach capital X2 colon small x2 using the addressing information capital X2 tick colon small x2 tick. At this point, a question arises as to which source address is contained in the packet heading to capital X2 colon small x2 to capital X1 colon small x1 or capital X1 tick colon x small x1 tick. If the NAT presents the hairpin packet to X2 with source addressing information capital X1 tick colon x1 tick, the NAT is said to have external source IP address and port hairpinning behavior. So if it contacts its own associated public IP address, if your router has two public IP address, it is said to have external source IP address and port hairpinning behavior. This behavior is required for TCP NAT. So this is actually what is happening right now in TCP NAT or in the real world. The justification for requiring this behavior is for applications that identify their peers using globally routable addresses. In our example, capital X2 may be expecting an incoming connection from capital X1 tick, which is the public routable address of capital X1 only, because of coordination from a third-party system. NAT editors. Together, packets using UDP and TCP transport protocols account for most of the traffic carried on the internet. The transport protocols by themselves can be supported by NAT without additional complexity because their formats are well understood. When application layer protocols used in conjunction with them carry transport layer or lower layer information such as IP address, the NAT problem becomes considerably more complicated. So for application like FTP where the application load actually contain the protocol and the IP address, this normal behavior of TCP or UDP protocols for most of the IP traffic is not acceptable anymore. The most common example, FTP, is normal in RFC 0959. In normal operation, it communicates transport and network layer endpoint information and IP address and port number so that additional connections can be made when bulk data is to be transferred. This requires a NAT to rewrite not only the IP addresses and port numbers in the IP and TCP portions of a datagram, so the NAT will not only rewrite the transport and the layer 3 but also some of the application payload itself. NATs with this capability are sometimes called NAT editors. So whenever you're trying to modify or the application load includes like the transport, it's not like a TCP anymore, the transport and IP. So if you not change the size of a packet's application payload, so if you change the NAT, you don't like you it's not a TCP because it's FTP. At the same time, it's not a normal behavior because for routers, their job is only translating IP and transport layer or transport protocol. If a NAT changes the size of a packet's application payload, considerable work may be required. For example, TCP numbers every byte in the data transfer using a sequence numbers. So if a size of a packet is changed, the sequence number also require modification. So NAT editor requires more work because it change the actual payload of the data. If you don't work around that, that data can be corrupted. So, or the data, the one or data format you actually send from your front end on your browser may not actually arrive the same way. Service provider, not SPNAT, and service provider IPv6 translation. A relatively recent development involves the idea of moving NATs from the customer premises into the ISP. This is also sometimes called service provider NAT or SPNAT, carrier grade NAT, CGNAT, we discussed in the previous video, or large scale NAT, and is intended to further mitigate the IPv4 address depletion problem. In its basic form, there is no functional difference between conventional NAT and SPNAT. The difference is really in the proposed domain of use. However, moving the NAT function from customer to ISP raises security concern and bring into question whether individual end users are able to deploy internet servers and control firewall policy. NAT traversal. As an alternative to the complexity of placing ALGs and NAT editors in NAT devices, an application may attempt to perform its own NAT traversal. So to avoid that NAT editor or modifying your NAT to be able to work around those FTP or unique protocol, some actually use NAT traversal. Instead of like using NAT, you're gonna contact directly. For example, for applications such as P2P, or live video call, you will need to traverse inside those private hosts. Not just you just don't want to know it's their public IP. Usually this involves the application trying to ascertain the external IP address and port numbers that will be used when its traffic passes through a NAT and modifying its protocol operations accordingly. So usually the application layer or layer 7 will ascertain the external IP and the port they will use to communicate with that or to assess that will be their way to communicate inside those private hosts they want to contact. If an application is distributed across network like has multiple clients and servers, some of which are not behind NATs, the server can be used to shuttle copy data between the clients that connect from behind NATs, or enable such clients to discover each other's NAT binding and possibly facilitate direct communication. So sometimes you're in the distributed network where you have NAT behind NAT, so it will be hard to traverse that. Therefore, you will need to have a server that will copy data between those clients securely that will help you to get into their direct communication. So this server will behind NATs will enable such client to discover each other's NAT binding and possibly facilitate direct communication. Using a server to copy data between clients is usually a last resort option because of the overheads involved and potential for abuse. So using this server actually the last resort, as we will see in the future videos. How turn is actually the last resort. We usually want to do it using hole punching or pinholes. Consequently, most approaches attempt to provide for some methods that allows direct communications. Direct methods have been popular for peer-to-peer file sharing, kind of like the what the FTP are used for, games, and communication application. Because for files, you really need to directly contact with host because you need to access with their file system, which is usually a kernel permission, or you need an admin permission because those you could introduce bugs or virus on their system. However, such techniques are often confined to a particular application, meaning that each new distributed application requiring NAT traversal tends to implement its own methods. This can lead to redundancy and interoperability problems. To combat this situation, a standard approach for NAT traversal has been established. So we will just discuss this in the future videos. Unsaf and yeah, these are long.